In the previous lecture, we have discussed in detail the violation of parity in beta decay. Actually, you have seen that according to the Li and Yang concept, the parity does not remain conserved in any weak interaction, although parity remains conserved in strong interaction, in electromagnetic interaction, and so many nuclear processes. But in weak interaction, parity does not remain conserved. In fact, today's lecture is also related to this parity violation. In fact, there is a parameter which is called helicity of the particle, and in terms of this helicity of particle, we will again see the concept of parity or the violation or conservation of parity in a nuclear process. In fact, Li and Yang suggested that the violation of parity in beta decay is a direct consequence of the longitudinal polarization of electrons and neutrinos. Okay, so we can discuss the parity violation in beta decay in terms of the helicity of the electron emitted in this process and the helicity of the neutrino. In fact, first of all, we will see how this helicity is defined in general. Then particularly we will actually calculate the helicity of electron and neutrino. Although in this lecture we will see only the calculation or determination of helicity of electron, but in the forthcoming lecture we will also see that how the helicity of neutrino is determined. So first of all, we will know what is this helicity. In fact, you can say that helicity is just a parameter in terms of which we can decide that in a nuclear process the parity will remain conserved or it will not remain conserved. So for that validity of the conservation principle of parity, we use a parameter which is called helicity. Actually, physically, this helicity represents the state and degree of polarization of particles. So you may say that helicity represents the state and the degree of polarization of particles and photons. Actually, we can also define the helicity of photons, although in this lecture our concern is with the helicity of electron particularly, but it may be defined for photons. So what is the basic definition of this helicity? First of all, we will see it. In basic form, a helicity is defined like this. It is denoted by the symbol H, and H is defined by this scalar product of two unit vectors sigma hat and p hat. Actually, H, which is equal to sigma hat dot p hat. What are these sigma hat and p hat? You can see. In fact, this sigma hat is a unit vector along the spin direction. Mark it. Sigma hat is just a unit vector and it is directed in the direction of spin. And p hat is also a unit vector and it is directed in the direction of linear momentum of the particle. And so you can say that this p hat is equal to the linear momentum vector p and its modulus p. Okay, these are the two unit vectors. Now you can see this scalar product sigma hat dot p hat may be either positive or it may be negative, it may be zero. And all those values of this scalar product, that is helicity, represents actually the different state of polarization. Okay, so let us consider some of the specific values of these scalar product. First of all, we consider that if these two unit vectors, that is the unit vector sigma hat directed along the spin and the unit vector p hat directed along the linear momentum. If these two unit vectors are parallel to one another, that is, they are directed in same direction, it means the spin direction and the linear momentum direction are same. In that condition, what will be the helicity? In accordance with the definition, you can see that H is equal to sigma hat dot p hat. So this H will be equal to sigma mod of sigma hat times mod of p hat times cos 0, because both of these vectors are parallel, so angle between these two vectors will be 0. And since sigma hat and p hat are unit vectors, so their moduli is simply equal to 1. So this will be 1 into 1 into 1, that is plus 1. Okay? And if the helicity comes out to be plus 1, then we simply say that beam of particles is longitudinally polarized. It means if the spin vector and the linear momentum vector are collinear, are in the same direction, then the beam of particle is called longitudinally polarized. Okay? And similarly, if you consider that the sigma hat is anti-parallel to p hat, it means the spin direction is just opposite to the linear momentum direction of the particle, then what will be H? From the definition you can see H will be again mod of sigma hat times mod of p hat times cos pi. Since these two vectors are in opposite direction, so angle between those two vectors are pi, and that will be equal to minus 1. Actually, this value of parity, of the helicity also represents that the beam of particles is longitudinally polarized. Okay? It means when the helicity comes out either positive and or negative, then the beams of the particle are longitudinally polarized. But if you consider that these two unit vectors are perpendicular to one another, it means sigma hat is perpendicular to p hat, it means the spin direction and the linear momentum direction are mutually perpendicular. In that condition, you can see the helicity will be what? This is mod of sigma hat times mod of p hat times cos pi by 2. But cos pi by 2 is 0, so helicity will be 0. And actually, this value of helicity represents that the beam is transversely polarized. Okay? This is just a simple concept. Now, as I have told you earlier that helicity is a parameter, and we decide the parity will remain conserved or its conservation will be violated in a nuclear process or in an interaction, that is determined in terms of helicity. So we simply say that this helicity is related to the parity violation. Okay? Now consider that this parity is a good quantum number. When you say that parity is a good quantum number, it means what? It means the system has a definite parity. Definite parity means the parity does not change. This may be either even or odd, but its value is definite. It means that parity remains conserved in the process. In fact, when the parity will have a definite value which may be either even or odd, in fact, then the helicity must be equal to 0. Helicity must be equal to 0. So you can simply say that if H is equal to 0, if H is equal to 0, this represents that parity remains conserved. This remains, parity is conserved. Or in other words, you can say when H is equal to 0, then parity is a good quantum number. It has a definite value, and that definite value may be even or odd. But just its converse, you can think that if this helicity is not equal to 0, so when helicity is not equal to 0, definitely parity conservation will not hold. Parity will not remain conserved, or in other words, we can simply say that if helicity is not equal to 0, parity must be violated in the interaction. Okay, so you will see that in beta decay process, the helicity is not 0, and that's why we can say that the parity does not remain conserved in the beta decay process or in any weak interaction. Okay, so this is a very simple fact in terms of helicity. We simply say that if helicity is 0, parity will remain conserved, and if helicity is not 0, then parity will not be conserved in the interaction. Okay, so H not equal to 0 implies that parity must be violated in interaction. Okay, now you know that polarization is basically of three types, that is linearly polarized light you have studied, circularly polarized light you have studied, and elliptically polarized light you have studied. And again, in accordance with the sense of rotation of the electric field vector in case of light, I am not talking about the polarization of electron beam or neutrino beam. In case of in optics, you have studied polarization, and then you see there that polarization may be polarized light may be linearly polarized, circularly polarized, and elliptically polarized. But in case of circularly and elliptically polarized light, there again the polarization is of two types, that may be left-handed or right-handed. Similarly, in this case, in nuclear physics, we simply say that if the particle rotates in clockwise sense as it recedes from the observer, then it is known as right circularly polarized. Mark it. When the particle rotates in clockwise sense and it recedes, it moves away from the observer, then we call the polarization as right circularly polarized. Okay. In fact, when the particle is right circularly polarized, then in nuclear physics we simply say that helicity is positive. Okay, in case of right circularly polarized particles, the helicity will be positive in nuclear physics. Actually, this is just the reverse definition as we find it in optics. Okay, so remember, RCP means positive helicity, and just opposite, you can say that if the particle rotates in anti-clockwise sense, at the place of clockwise sense, now I am telling you that if the particle rotates anti-clockwise sense as it recedes from the observer, then actually it is known as left circularly polarized. And if it is left circularly polarized, that means the helicity will be negative. So LCP means negative helicity in nuclear physics. So remember, RCP, that right-handed circularly polarized, in that case helicity is positive, but in case of left-handed circularly polarized, the helicity is negative. Okay, so this was a basic concept of helicity in general, and you have seen and you must remember that how we can decide that in a nuclear process the parity will remain conserved or not. You have to simply see the value of helicity of the particle involved in the interaction, and if you find that helicity is equal to 0, then parity will remain conserved. That it means the parity will be a good quantum number for that process, and its value will be definite. That value may be even or odd. But if helicity is not equal to 0, then there will be definitely a violation of parity. It means for that process the the parity will be not a good quantum number. Its value will not remain at a particular definite value. Okay. Now in particular we will see how the helicity of electron is determined in beta decay process. You know, in beta decay process electron and positron are actually emitted. So in this section we will discuss the determination of helicity of electron and positron too. By the same experiment, helicity of electron and positron are determined. Okay. So first of all, you have to know what do you mean by helicity of electron in beta decay. Actually, in beta decay process, the helicity of electron is defined as the component of polarization along the direction of motion of the electron. Component of polarization in the direction of motion. So if you consider that the motion of electron is in this direction, it means it is its direction of velocity. So you have to find the component of polarization, and let us say that this electron is polarized in this direction. Then we have to simply find what will be the component of this polarization in the direction of motion of electron, and that component of polarization in the direction of motion of the electron is called helicity of electron in beta decay. Okay. Actually there are several methods to determine the helicity of electron in beta decay, but here in this lecture I will just give you a brief explanation or brief calculation of helicity of electron based on a famous experiment done by Moeller, and this Moeller experiment is actually electron scattering. So from a large number of methods for determining the helicity of electron, we are going to discuss only one experiment, and that experiment is Moeller scattering experiment or Moeller scattering method for determination of the helicity of electron. And as I have told you that this is just an electron scattering experiment. Okay. The schematic diagram for the experimental arrangement I have shown here in this figure. You can see this is just a source of electron. Source of electron means source of beta particles, and there will be a beta active nuclei, and that will suffer beta decay, and in that beta decay process electrons are emitted, and the emitted electrons actually fall on a monochromator. Okay, and from this monochromator the impinged electrons passes through this monochromator, and you can see this rectangular coil is just actually a foil of ferromagnetic material, and this can be magnetized in a particular direction. So this rectangular foil is made up of ferromagnetic material like iron, cobalt, nickel, and it is magnetized. You can see this arrowhead actually represents the direction of magnetization. So the electrons from this monochromator falls on this foil of magnetized ferromagnetic material, and actually the direction of magnetization of this foil may be reversed, and it is necessary to just reverse the direction of magnetization in this experiment. In fact, it is found that if the electron incident on this monochromator provides almost half of its energy to the scattered electron, then actually after scattering from this foil, two electrons will get scattered. So you can see this is your scattered electron 1 and this is scattered electron 2. Okay, and these scattered electron, I have mentioned all these facts here. You can see I am just giving a reading here that the electron passing through the monochromator impinge on the magnetized ferromagnetic foil. If the fractional energy transfer by the incoming electron to the scattered electron is 1 by 2, it means the incident electron provides almost half of its energy to the scattered electron, then it is seen that the two electrons with equal energy leave the foil. Okay. Now these scattered electrons are counted in coincidence. You can see there is a coincidence circuit here, and these are the counters. This is counter number 1 and this is counter number 2. Actually these two counters count the number of electrons passing through it, and for this, when these two electrons get coincident, then with the help of this coincidence circuit, this number is actually found. Okay, so if you consider that F is the fraction of electrons polarized in the scattering foil and alpha is the angle of inclination of the foil to the electron beam, then the relative change of the coincidence counting rate on the reversal of magnetization of the foil is given by this formula. Actually, as I have told you, that when the electrons are incident on the foil, then the foil is magnetized in a particular direction, and with the help of the counter we simply find the counting rate and the number of electrons passing through it, and then that is counted for a particular time. Then the direction of magnetization is just reversed and again the same calculation is done. So when the direction of magnetization is reversed, then there will be a change in the counting rate, and what is that change in counting rate? That is denoted by this symbol delta. So this delta actually denotes the relative change of the coincidence counting rate, and this relative change of counting rate after the reversal of the direction of magnetization of the foil is given by this formula. Remember this formula. This is equal to 2r pi times f into cos alpha. Now we will see what are the different quantities in this expression. Actually, you can see that this pi denotes the helicity of the incoming electrons, and our aim in this experiment is to measure this pi. Pi is to determine. Okay, so you can see what will be this pi. Pi will be equal to delta over 2r f cos alpha. So if all the quantities in RHS is determined in this experiment, then substituting those values in this equation, you can determine the helicity of the incoming electron. First of all, you have to know what are the different quantities used in this equation. You can see this R is defined as 1 minus sigma p over sigma a and divided by 1 plus sigma p by sigma a. Okay, R is defined as 1 minus sigma p by sigma a over 1 plus sigma p by sigma a. And what is this sigma p by sigma a? In fact, here the subscript p refers for parallel word and a for anti-parallel word. In fact, sigma p by sigma a, you can see this is actually the cross-section ratio for the electron scattering with spins parallel. This sigma p represent the p later represent the parallel spin, and a refers the anti-parallel spin. So what is this sigma p by sigma a? You can see this is cross-section ratio for the electron scattering with spin parallel and anti-parallel. Okay. And what is this F? In fact, F is equal to ms over n into mu. Remember it. F is equal to ms over n into mu. What is this ms? Actually, ms is the magnetization produced in this ferromagnetic material. And when you say magnetization, that means this is magnetic moment per unit volume. Okay, magnetic moment per unit volume due to the electron spin. Actually, magnetic moment is also due to orbital angular momentum or orbital motion of the electron. But this ms is the magnetization of the material due to the electron spin. And when you say magnetization of the material due to electron spin, that means it is simply the magnetic moment induced in the material per unit volume. Okay, magnetic moment induced in the material per unit volume. This is ms. And what is this n? N is simply the density of electrons in the material. It means this is number of electrons per unit volume. Okay, and mu represents the Bohr magneton. You know, actually Bohr magneton is just a natural unit to measure the magnetic moment. So this quantity F represents ms over n mu, where ms you have seen that this is actually the magnetization due to electron spin, n is number of electrons per unit volume, and mu is Bohr magneton. Okay. Now, as you can see, if you want to measure the helicity pi of the incoming electron, definitely you have to measure all the quantities present in this equation in RHS. That is, first of all, we have to measure delta in this experiment, and after measuring delta, we can find the value of pi. So you can see delta will be measured how? As I have told you that first of all, magnetization is actually applied in a particular direction, and counting rate is noted by the counter and in a particular time, and after that time the direction of magnetization is just reversed, and again the same calculation is done. It means again we will find the counting rate in the same time interval, and the difference of those two counting rates will give the value of delta. So you can see I have mentioned it here that to determine delta, the foil is first magnetized in one direction. Okay, and coincidences are recorded. Okay, and for a known time, the magnetization is reversed and coincidence rate is further measured, and the difference of these two readings gives the value of delta. Okay, but here in the original experiment performed by Moeller, what was the result? I am just mentioning that this result is found from the experimental data. You can see that the this method, as I have told you earlier, is equally used for the determination of helicity of electron as well as positron. It means this method is suitable not only for the determination of helicity of electron, but it is also a suitable method for the determination of helicity of positrons. In fact, experimental data show that electrons in beta decay are left-handed and positrons are right-handed. Okay? And in allowed transition, after calculation in this experiment, it was found, I am mentioning directly that result. I have not calculated it, but from the experimental data of this experiment, you can say that helicity H is equal to minus V over C, where V is actually the velocity of electron and H is equal to plus V by C. Both are possible. So you can simply say that H is equal to minus plus Vc. Don't write it separately. You can say that H is equal to minus plus Vc, and that was obtained, that was seen in this experiment. Actually here this minus sign is for the left-handed, this minus negative sign implies left-handed and positive sign actually represents right-handed. Okay, so in fact in this experiment it was seen that the electrons emitted in the beta decay are left-handed. This so you can say that the helicity of the electron is equal to minus V by C. This is the helicity of electron. I am writing it in fact He. And the helicity of positron, it was found to be plus V by C. Okay, so if the velocity of the electron and or positron is known, the helicity can be calculated, and you can see that the helicity of electron is negative and helicity of positron is positive, and it is not zero. And as I have told you earlier that if H is not equal to 0, H is not equal to 0, definitely parity in that process will not remain conserved. So after the measurement of the helicity of electron emitted during the beta decay process, it was seen that helicity of electron is not 0, helicity of positron is also not 0, and if it is not 0, definitely parity will be not a good quantum number in this process. It will not remain conserved, and that's why we simply say that in terms of helicity, that since the helicity of electron is not 0, so we can say that parity will not remain conserved in the beta decay process. So I hope you have understand that this helicity is a parameter. It is a parameter in terms of which we decide that in a nuclear process the parity will remain conserved or not. Okay, so I think you have understand. In the forthcoming lecture we will see some of the more important concept of this nuclear decay processes.